What if we told you that the future of machine learning and neural networks could be shaped by a network of nanowires? Yes, you heard it right. The realm of machine learning and neural networks is about to experience a seismic shift. Normally, these networks learn from vast amounts of data, stored and processed to make predictions or decisions without being explicitly programmed to perform the task. But imagine a system that learns and remembers in real time, without the need for data storage. This is no longer a figment of our imagination, thanks to the pioneering work of Professor Zena and her team at the University of Sydney. They've developed a physical neural network, a lattice of intersecting nanowires creating neuromorphic components called memristors. This network is capable of carrying out memory and learning tasks, reshaping our understanding of machine learning and neural networks. Now let's dive into the development of this groundbreaking physical neural network. The birth of this physical neural network begins with an intricate network of nanowires. Imagine a bustling city with roads crisscrossing and intersecting, much like the veins under your skin. Now, shrink that city down to a microscopic level, and you have a rough idea of what nanowires are. They are incredibly tiny conductive wires, often made from materials like silver or carbon, and they are the backbone of our physical neural network. These nanowires don't just exist in isolation. They form an intricate, complex network, intersecting and connecting at various points. Just like in a city where roads intersect to form junctions, the nanowires intersect to form junctions too. But these aren't ordinary junctions. These are the birthplaces of something extraordinary, neuromorphic components, otherwise known as memristors. Now you might be wondering, what on earth is a memristor? In the simplest terms, a memristor is a device that remembers. It's a resistor with memory, hence the name memristor. The fascinating part about these memristors is their ability to carry out memory and learning tasks. They do this using simple algorithms that respond to changes in the electronic resistance at the junctions where the nanowires intersect. It's a lot like how our brains work. Just as our brains use neurons to process and store information, the physical neural network uses memristors. But instead of using biological processes, these memristors use changes in electrical resistance. So in essence, the birth of the physical neural network begins with nanowires. These nanowires intersect at various points to form memristors, which are the building blocks of our physical neural network. Just as bricks and mortar are the building blocks of a house, memristors are the building blocks of this network. The creation of these memristors was just the first step in the development of this innovative physical neural network. But the journey doesn't stop here. Stick around to find out how these memristors play a crucial role in the learning efficiency of the physical neural network. Memristors, the heart of this physical neural network, play a crucial role in memory and learning tasks. So what exactly is a memristor? It's a nanowire component that behaves rather like a human neuron. When two nanowires intersect, they form a memristor, a neuromorphic or brain-like component. It's like a junction where information can be stored, processed, and recalled, much like the synapses in our brain. These memristors carry out memory and learning tasks using simple algorithms. But you may wonder, how do they do this? Here's where it gets interesting. The algorithms respond to changes in the electronic resistance at the memristor junctions. This means that when an electric pulse passes through a memristor, it changes the resistance at that junction. This change can be read as data, allowing the memristor to remember the pulse. Let's think of it like this. Imagine you're trying to navigate through a maze. Each time you reach a dead end, you mark it in your memory. When you encounter the same dead end again, your brain recalls the previous encounter, and you choose a different path. This is essentially how memristors work. They remember the electrical pulses they've encountered before and respond differently based on that memory. This is what makes memristors so vital in the physical neural network. They are the network's memory keepers and learning facilitators. They enable the network to recognize patterns, learn from them, and recall them when needed. This is how the network can recognize and remember sequences of electric pulses that correspond to images. So we can say that memristors are the magic behind the physical neural network's learning and memory capabilities. They represent a breakthrough in our understanding of how to mimic the brain's learning process in a machine. With the help of memristors, this physical neural network demonstrated an impressive ability. They have paved the way for a future where machines can learn and remember in real time, without the need for extensive data storage. It's a future that is efficient, low energy, and holds immense potential for more complex real-world learning and memory tasks. The physical neural network's learning efficiency is nothing short of exceptional. Let's delve into this in more depth. At the heart of the network's prowess is its ability to recognize and remember sequences of electric pulses that correspond to images. It's an impressive feat that mirrors the way our own brains process visual information. Imagine this, a cascade of electric pulses, each one different from the last, flowing through a network of nanowires. Each pulse represents a different image, a different piece of information to be processed. As these pulses move through the network, they encounter the neuromorphic components, the memristors, at the intersections of the nanowires. The memristors respond to these pulses, adjusting their electronic resistance in real time. This change in resistance is akin to the neural network learning. It's the memristor's way of saying, I recognize this pulse, this image. And every time the same pulse passes through, the memristor's response becomes more refined, more precise. It's learning, remembering, and adapting, just like our own brains do when we encounter new information. But here's the truly astonishing part. This physical neural network doesn't just recognize and remember these electric pulses, it does so with a learning efficiency of 93.4%. That's right, over 90%. This is an incredible level of efficiency, particularly when you consider that this all happens in real time, with no need for data storage. Now you might be thinking, that's great, but what does it all mean? Well, it means that this physical neural network is capable of learning and remembering information at a rate that far surpasses many existing artificial intelligence systems. It's a breakthrough that could have far-reaching implications for the world of machine learning and neural networks. This high learning efficiency could revolutionize the future of machine learning and neural networks. And that's not just a bold claim, it's a glimpse into a future where artificial intelligence can learn and adapt in real time, just like us. The potential impact of this physical neural network is vast and transformative. Imagine a world where machine intelligence is more efficient, consumes less energy, and can handle complex learning and memory tasks in real time. This is the promise of the physical neural network, developed by Professor Zdenka Kunchik and her team at the University of Sydney. One of the most significant impacts lies in the realm of efficiency. Traditional artificial neural networks require vast amounts of data storage to learn and remember. With this physical neural network, learning and memory tasks are carried out in real time, without the need for data storage. This could mean smaller, more compact devices capable of sophisticated machine learning tasks without the power and space demands of current systems. But it's not just about efficiency, it's also about the potential for more complex learning. The physical neural network has demonstrated an impressive learning efficiency of 93.4% in recognizing and remembering sequences of electric pulses that correspond to images. This suggests that the network could be used for more complex real-world learning and memory tasks, expanding the possibilities of what machine learning can achieve. As we look towards a future increasingly driven by artificial intelligence, the need for low-energy, efficient machine intelligence becomes ever more critical. The physical neural network could pave the way for this future, enabling more sustainable and scalable AI solutions. Imagine smart cities powered by low-energy AI, or personalized learning systems capable of adapting to individual learning styles in real time. Furthermore, this breakthrough could have a profound impact on industries like healthcare, where real-time data analysis and decision-making can literally save lives. Or in the field of environmental science, where efficient monitoring and prediction systems can help us better understand and tackle climate change. The potential applications are as vast as our imagination, and the physical neural network could be the key to unlocking these possibilities. The future of machine learning and neural networks is indeed exciting, thanks to the development of this physical neural network.